Hello, and today I wanted to make a video to explain the circuit that I'm demonstrating. And really we're pulling material from two different domains. Differential equations and analog electronics. In the 7th chapter of the differential equations book, chaos is introduced. Let's go to section 7.6. Here we are. 7.6. And these are the Lorenz equations. So it's lambda x, lambda x negative x plus y is equal to dx dt. Dy dt is equal to rx minus y minus xz. And dz dt is going to equal negative bz plus xy. So it's these three equations. And it states that b is going to be 8/3. So this is going to be 8/3 here. There's no coefficient there. Alright. Lambda, well, lambda is going to be 10 for the atmosphere. Again, that's stated in the text. R here can vary, but when R is going to equal 28, that is when we'll get the characteristic chaotic system. Now, the text uses computer-generated plots, and it goes into more depth than this. But ultimately, the trajectory looks something like this. Let me zoom in here real fast. I'm unfocused on you. Alright. Or, the characteristic x versus z owl's face of the Lorenz equations. See, r equals 28 in this instance. Now, these use digital computers to generate the plots. But, as I will show you, there's another way to do it. Now, I'm going to jump to electrical engineering. And it might seem an arbitrary field, but it's not. I mean arbitrary for the purposes of this problem. Now, when we reference this text, which is the standard, this book is Electronics, Introduction to Electronic Circuits, 9th edition, I'm sorry. It's the Intro to Analog Electronics for all EE's Tech. Now, here we get to the 7th chapter, and actually, this is covering operational amplifiers. This is page 293. So with this circuit, a 1 megohm across a 1 microfarad capacitor, the output is the negative time integral of xt. So I think, this is interesting, but can we use it? And the answer is yes, indeed. It turns out that you can make a general purpose integrator, and it's actually shown on this page right here. That's 297, and it follows the schematic in the upper left you can see here. Only we're not going to put R2 because that doesn't make much sense for our purposes. So basically, when you have a resistor junction across an op amp, and again, these are just notational symbols here. The negative is the inverting input, the positive is the non-inverting input. And then you can put a capacitor across it. No, I'm sorry. This is. No, wait. That's right. The positive's at ground. And So then we'll call this one R1, R2, and you can add other ones. Let's assume there's an R3. Now, what is the output going to be? Assuming we have a switch which can reset the capacitor at an arbitrary time, and we'll see later that's not necessary to make the Lorenz circuit work, then the output is actually going to be equal 1 divided by, this is the capacitance of C, R1C, obviously integrated negative because that's an inverting circuit, 0 to T. Again, the voltage at what we will call this voltage node A, B, and C. And this would be the voltage at A. I'm sorry. Voltage at A, dt, or really this would be VA of tau d tau, plus of course the remaining terms in the like fashion, 1 divided by negative 1 divided by R2C multiplied by the integral of 0 to T, it's the time integral of VB tau d tau. And you would just continue in like fashion to add the terms. Okay, so now we have a means to integrate. So to implement this, if we integrate these on both sides, then this would equal x, this would equal y, and this would equal z. Plus, of course, the arbitrary constant, but let's ignore that for now. So if we were to take this circuit and add the right resistors and capacitor values, then we could, in theory, make these integrals. See, negative constant times difference. Now, the problem is you have an xy and an xz, where these are two arbitrary voltages. Now, this requires the use of something called an analog multiplier, which you can actually make with logarithmic amplifiers and op amps, but it's better just to buy an AD633, and they're about 10 to 12 each. And so the circuit that I've made does this, and on the next page I'll show the schematic.